Okay, so let me quickly recall where our discussion is at this point of the course. So we have this this function lambda of tau. So this we have this function lambda defined on the upper half plane with values the complex numbers. Lambda of tau was defined as E3 of tau minus E2 of tau by E1 of tau minus E2 of tau, and we are trying to see. So this function is invariant only for the action of the congruence mod 2 subgroup, and we are trying to study the mapping properties of this function. So the theorem that we are trying to prove is the following, that see if you take the following region, the complex plane. So this is the tau plane, and we have so this is so this coordinate is 1, and well this is the line real part of tau equal to 1. This is of course the imaginary axis, this real part of tau is equal to 0, and then we take a semicircular arc which is centered at half and radius half, okay, and we take this region omega, okay, we take this region omega which is bounded by which is bounded on the left by the imaginary axis, okay, and on the right by this line which is real part of tau equal to 1, and below by this semicircular arc, alright. And the claim is that lambda gives us an isomorphism of omega onto the upper half plane, okay, and the isomorphism is in such a way that so it's an isomorphism, it's a holomorphic isomorphism, okay, so it's a holomorphic isomorphism of omega onto the upper half plane, alright, and the under this this isomorphism can be extended to the boundary continuously, okay. So you can define omega on the you can define lambda on the boundary, so that the boundary is mapped to the boundary of the upper half plane, namely the real axis, okay. So if I draw this diagram, so I am taking the transformation omega equal to lambda of tau, and the corresponding the image plane is the omega plane, and the claim is that this region omega is mapped into the upper half plane. So this is also the upper half plane here, it is also the upper half plane there, so it is mapped here onto the upper half plane here, and in such a way that the boundary is mapped onto the real axis, alright. So so that is what we have to prove, alright, this is what we have to prove, and so we started out in the previous lecture by proving that lambda is real on the boundary, okay. The problem with the boundary is only at these 2 points, at 0 and at 1, okay, because you see lambda is anyway analytic on the upper half plane, so it's defined on this on the imaginary axis, okay, in the upper half plane. The problem is at 0, okay. Similarly there is no problem along all the points of this semicircular arc, the problem is only at 0 here and at 1 at the point 1 there, alright. So what one has to show is that lambda approaches a proper limit at 0 and at 1, and the limit and that limit is achieved no matter how you approach it, so long as you are inside this region or in the boundary of that region. Okay, that is what you have to verify, and you should verify it for the limit here as well as for the limit there. Okay, and in fact what I had said yesterday was that I mean in the last lecture was that you see the fact is, as tau goes to infinity, okay, in particular as tau so since we are considering only this portion of the vertical strip, okay, as tau goes to infinity, essentially you are letting imaginary part of tau go to infinity, okay, then the fact is that it should give you the value of lambda at infinity, and that turns out to be 0, okay, and the value of lambda at 0 turns out to be 1, okay, and the value of lambda at 1 turns out to be infinity, and this is how lambda is supposed to map the boundary of omega onto the real axis. Okay, so of course I have already shown, except for the point 0 and 1, that lambda is real on the boundary of omega. That was done in the previous lecture. So this lecture is essentially to study the behavior of lambda as you approach 0 or as you approach 1. Okay, so let me write down immediately what our claim is. Our claim is the following. Our claim is as so yeah, I will draw another diagram if I need one. So as imaginary part of tau tends to infinity, okay, as imaginary part of tau tends to infinity, so in fact I should say as imaginary part of tau tends to plus infinity, okay, because this is a real variable, alright, lambda of tau tends to 0, okay, and the way it tends to 0, you see, is uniform as a function of real part of tau. Okay, so you see, as you let imaginary part of tau tend to infinity, lambda of tau will essentially be thought of as a function of real part of tau, alright, and the way it tends to 0 is uniformly with respect to the real part of tau. So let me write that down, uniformly with respect to real part of tau. Okay, so this is the claim. Now so this is the first claim, all right, and how are we going to prove this? So this will tell you that the value of, you can define the value of lambda at infinity as 0, okay, you can define the value of lambda at infinity at 0, and that is how lambda takes the value 0 in the image, alright. So and of course you see, if you think of this complex plane as the Riemann sphere, then infinity is actually corresponds to the north pole on the Riemann sphere, so it is really a point, okay, in that sense by the stereographic projection, and all we are trying to say is that lambda can be extended to the point at infinity by defining it to be 0, okay, because this allows us to do that, right. So well, so how does one prove this? So in order to prove this, one has to do some work with series, okay. So let me begin with the following statement, we will need to use sine pi squared by sine squared pi z is sigma m equal to minus infinity to infinity 1 by z minus m the whole square. So we need to use this this identity, okay. So we will have to use this identity. You can realize why we will need it, because you see this is the this is what partly appears when you write out the formula for the phi function, right. So so the first thing is let us first justify this identity, okay. See, you see the LHS, the left hand side, if you look at the function here, this function is analytic everywhere except the points where the denominator vanishes, and the points where the denominator vanishes are precisely the integers. So you see LHS is analytic in C minus Z, okay. In you take away the integers from the complex numbers. So you see this is so here I should say Z, this is valid for C minus Z, okay. This is valid for any Z which is not an integer, okay. So the left hand side is of course analytic in C minus Z. What happens at points of Z? At points of Z you get by Z I mean integers, at integer values you get poles of order 2, okay. At each value Z equal to m, the LHS, the left hand side, has a pole of order 2, it has a pole of order 2, and further, and you know of course if you have a isolated singularity then you have a Laurent development, and if you take the Laurent development about Z equal to m, that means you try to expand in powers positive and negative of Z minus m, then the singular part will be precisely 1 by Z minus m the whole square, okay. So at each value Z equal to m, the left hand side has a pole of order 2 and has singular part 1 by Z minus m the whole square. This will be the singular part, okay, this will be the singular part. So this is quite obvious. Now but you look at the right side, in the right side you are simply adding all those singular parts together, okay. The right side I have written just by adding all those singular parts, okay. But the nice thing is I cannot just write down something like this and expect it to define something sensible, but in this case it really does. See the term on the right side is actually a convergent series. In fact if you take mod y greater than or equal to 1, okay, then this will be uniformly convergent, okay. I just have to stay away from the integers, alright. So the RHS, the right hand side, converges uniformly for mod y greater than or equal to 1, let us say, okay. You see the point is you see if you look at if I draw a diagram, the situation is like this. I have see I have, this is a complex plane, you see I have so this is C, this is the Z plane, and you know I have all my integers here, so I have all my integers here, okay. See mod y y equal to 1 is a is going to be line parallel to the x-axis. So mod y greater than 1 is going to be either so it's going to be this region, it's going to be this, and it's going to be this. So this will be the region, this will be the region mod y greater than or equal to 1, okay. And the point is that if you take that region, then you can compare the part of the series from 0 to infinity and the other part of the series from say -1 to -infinity separately with sigma 1 by n squared, which is convergent, okay. So you can, by using the Weierstrass M test, you can actually confirm that this is uniformly convergent, alright. So the right side also converges uniformly for mod y greater than 1, alright. Now well, now so you see we want to prove the left side is equal to the right side, alright, which is the same as trying to show that the left side minus the right side is 0, is identically 0. Now let us look at the left side minus the right side, okay. Look at g of z is equal to the left hand side minus the right hand side. Look at this function, okay. Look at this function, alright. You see this function, if you take a point which is not an integer, okay, this is going to be an analytic function, okay. This is going to be an analytic function because both sides are, of course, both entries are analytic, okay, so long as z is not an integer. Therefore this is going to be an analytic function, and the fact that this series is an analytic function is because of uniform convergence, okay, and because each term of the series is analytic, alright. So this function is going to be analytic in, of course, c minus z, but more importantly, if you take points of if you take integer points, you see the singular part of this at z equal to m is already here. So when you subtract, the singular part is removed. So you see, if you concentrate at z equal to m, it will become a removable singularity, z equal to m will be a removable singularity. So as a result, this function will be an entire function, okay. So we at z equal to m, g of z has a removable singularity, in fact I should, it's actually analytic, okay. I am saying it's a removable singularity because I do some local analysis, and if I take a Laurent expansion, then the singular part I will get here is 1 by z minus m the whole squared. The rest of it is all analytic for z in a small neighborhood of m, alright, because z is not going to be any other integer other than m, and this is, of course, if you take the Laurent development at z equal to m, the singular part is going to be 1 by z minus m the whole squared. So if you take the difference, the singular part is going to go away, so which means you have only the analytic part, okay, and that is a way of saying that it is actually a removable singularity. In fact, you can actually say it is analytic, okay. So at z equal to m in z, so g of z is entire, so it's an entire function, this function is an entire function. That's the first observation. The second observation is, you see, if I replace z by z plus 1, the left side is not going to change, okay. in other words you see this function on the left side is periodic with period 1, and the same is true with the function on the right side, because if I replace z by z plus 1 I will still get the same series, okay. So the fact is both the left hand side and the right hand side are singly periodic functions with period 1, okay, and therefore their difference is also a periodic function with period 1, okay. So let me write that down. Now since the LHS and the RHS are periodic with period 1, so is G of z. So you see the difference which is G of z is actually periodic with period 1, okay. Therefore so its values are completely controlled by the values in a vertical strip of length 1, of horizontal length 1, okay. So you see the values of G of z are the same, are those that it takes in say 0 less than or equal to real part of z less than or equal to 1, okay, in this vertical strip, okay, because it is periodic with period 1. Now now you see what we are trying to do, we are trying to show LHS equal to RHS, we are trying to therefore show that this analytic function is 0. So what we would do, what we will try to do, we will try to show that G of z is bounded in this vertical strip, then by periodicity is bounded on the whole plane. Liouville's theorem will tell you that G of z is a constant, you evaluate that constant and then show that the constant is 0. That is how you prove G of z is identically 0, alright. So that is that is what we are going to do. So you see the point is that now you notice the following thing, see if modulus of imaginary part of z tends to infinity, okay, that is if you write z is equal to x plus iy and you let mod y tend to infinity, then you see the left hand side goes to 0 uniformly, then the left hand side goes to 0 uniformly in real part of z, okay. Right, it goes to 0 uniformly, alright, and that is basically because you see you have a you must all be familiar with this with the fact that we may use sin squared pi z, well if you expand it, it is cos h squared pi y minus cos squared pi x, okay. These are elementary identities, okay. So you see you can use this to infer that, this is very easy to see, alright. On the other hand, look at the right hand side, that is look at this series for mod y, namely for modulus of imaginary part of z greater than or equal to 1 is uniformly convergent in it's uniformly convergent in x, okay, and you see because of uniform convergence of this series you can take individual limits instead of taking the limit as mod y tends to infinity of this whole thing, you can take mod y tends to infinity for every term and then take the sum. But you see, as mod y tends to infinity of every term, it goes to 0, alright. So obviously this sum goes to 0. So the fact is this the right hand side, that also tends uniformly to 0 as mod y, namely modulus of imaginary part of z tends to infinity, okay. So the RHS namely so here I should say of course by the LHS I mean pi squared by sin squared pi z, and here by RHS I mean that series sigma m equal to minus infinity to infinity 1 by z minus m the whole squared tends to 0 uniformly if uniformly as modulus of imaginary part of z tends to infinity in mod y in modulus of imaginary part of z greater than or equal to 1, okay. So the moral of the story is that if you look at this vertical strip 0 less than or equal to real part of z less than or equal to 1, okay, then so you see so it's going to be like this. So this is my vertical strip, okay. If you look at this whole vertical strip, then your function g of z is bounded, okay. See at infinity it's going to go to 0, okay, and then so that means what does it mean? It means that its value can be its modulus can be made less than any arbitrarily given small epsilon beyond a portion above and below the strip, and for the remaining portion that is left out, that's anyway a compact region, and it has to have a bound. A continuous function on a compact set has to have a bound, okay. Therefore the upshot of this is that g of z is bounded in this period strip, okay, and since it is periodic with period 1, consequently it is bounded on the whole complex plane, and now Liouville's theorem will tell you that it has to be a constant. And what is that constant? That constant has to be the same, and if you now let modulus of imaginary part of z tend to infinity, that constant has to remain the same, so it has to be 0. So g of z becomes identically 0, and we have proved that the left side is equal to the right side, okay. So let me write that down. Thus g of z is bounded in 0 less than or equal to real part of z less than or equal to 1, hence bounded in C as it has period 1, hence is a constant by Liouville's theorem. Okay, and that constant turns out to be 0 if you let mod y tend to infinity, okay. That constant is equal to 0 if we let modulus of imaginary part of z tend to infinity, okay. Thus the left hand side is equal to the right hand side, okay. So that proves this formula, alright. Now the point is that we have to use this formula to get this claim, right. So we will do that next. So what we are looking at is so we are trying to study what happens to lambda of tau as the imaginary part of tau goes to infinity, alright. So lambda of tau is E3 of tau minus E2 of tau by E1 of tau minus E2 of tau, alright. So let us calculate what is what the numerator is. So E3 of tau minus E2 of tau is, if you remember, E3 of tau is the phi function evaluated at 1 plus tau by 2. So this is p tau evaluated at 1 plus tau by 2 minus p tau, the phi function associated with tau evaluated at tau by 2. This is what it is, and well, we can expand it. This turns out to be 1 by 1 plus tau by 2 the whole squared plus sigma omega not equal to omega in the lattice, omega not equal to 0, 1 by 1 plus tau by 2 minus omega the whole squared minus 1 by omega squared. This is the expansion of the first term, and then I will have to write out the second term. So I will get minus 1 by tau by 2 the whole squared plus summation over omega in L of tau, omega not equal to 0, of 1 by tau by 2 minus omega the whole squared minus 1 by omega squared. Okay. So all these series are uniformly convergent, and in fact I can get rid of these terms, alright, and you can notice that when I put omega equal to 0, I can put omega is equal to 0 here. If I put omega equal to 0 here, I get this term, okay. So I can push this term also into the summation and remove the restriction that omega is not 0. The same thing can be done here. So this simplifies to summation over omega in L of tau, omega not now I remove the restriction omega is not 0, and I simply write 1 by 1 plus tau by 2 minus omega the whole squared minus 1 by tau by 2 minus omega the whole squared. So this is what I get, okay. And now the trick is, if you want to use this, you change from summing over omega in the lattice to summing over pairs of integers, okay, because for omega in the lattice, after all, omega is of the form n plus m tau. So we rewrite this as a double summation, alright. So what one does is this is equal to, so now I will write it as summation over n equal to minus infinity to infinity, another summation over m equal to minus infinity to infinity, okay, and I write that as 1 by, now you see I am putting omega is equal to m plus n tau. So what I will get is I will get 1 plus tau by 2 minus m plus n tau the whole squared minus the other term, which is 1 by tau by 2 minus m plus n tau the whole squared. So this becomes summation n equal to minus infinity to infinity, summation m equal to minus infinity to infinity of so I end up with half, so I can write it as m minus half so I will get half minus m, I will write it as, okay, let me write it first as it is, half minus m is the real part, and coefficient of tau is going to be half plus half minus n into tau the whole squared, minus the other term is going to be, well, I am going to get minus m plus, well, half minus n into tau the whole squared. This is what I am going to get. And now you see, yeah, so now we are in good shape. You see, just look at only the forget the outer summation in the n, look at the summation only in m, and use the fact that summation from m equal to minus infinity to infinity of 1 by m minus z the whole squared is pi squared by sine squared pi z, which is what we proved. Okay, so you use that summation m equal to minus infinity to infinity of 1 by half minus m the whole squared plus, well, half minus n into tau the whole squared is summation m equal to minus infinity to infinity. What I am going to get is 1 by m minus there is no square here, yeah, there is no square here, so it is going to be m minus half. Alright, so if I switch the sign here, it is m minus half. If I switch the sign here, it is n minus half. Okay, times tau. So I guess this, I hope this is right, and of course that's a whole square, right? Because so I get m minus half, which is half minus m. The other one is n minus half. It should be n minus half into tau, is that right? So there we have m minus half. If I switch the sign, I get half minus m. There I get minus of n minus half tau. If I switch the sign, so maybe this should be half minus n here. This is half minus n. Okay. So well, if I apply that formula, then I will get this is pi squared by sine squared pi times this whole thing. So I will get half plus half minus n into tau. This is what I get. Okay, now if I use the summation, that summation formula, and of course, you know, if I take sine squared, if I push the pi inside, then I can change this sine squared to cos squared, and then I can write that as n minus half tau. So this finally becomes pi squared by cos squared pi into n minus half tau. This is what you will get finally. Okay, so that is what you get of the first term. All right, and what you get of the second term, let me write it down. So I will get sigma m equal to minus infinity to infinity. The second term is, suppose I calculate 1 by so that is minus m plus half minus n. I switch signs throughout, so I will get m minus half minus n times tau the whole squared, right? If I switch signs, that's right, and this is going to be pi squared by sine squared pi. By that formula, it's going to be half minus n into tau, which for uniformity with the previous, with this one, I write it as pi squared by sine squared pi n minus half tau. Okay, so this is where we have used the formula that we just recently proved. Well, we will end up with E3 tau minus E2 tau is equal to, there is a summation outside, summation n equal to minus infinity to infinity, and what you get inside is this minus this. Okay, So it is going to be pi squared by cos squared pi n minus half tau minus pi squared by sin squared pi n minus half tau. This is what you get, okay. And you see now you can see that if I let the imaginary part of tau go to infinity, okay, then you can see that each term is going to go to 0, okay, and therefore this quantity on the left will also go to 0, given that the series on the right side will converge uniformly. So you can take the term wise limit, okay. So the fact is, of course, you can easily verify that the modulus of the denominators, okay, that goes to infinity as imaginary part of tau goes to infinity, right. That is a very simple exercise, right. Therefore so what this will tell you is that as imaginary part of tau goes to infinity, okay, this will go to 0 and it will go uniformly to 0 in the variable real part of tau, okay. And the fact is you can take the term wise limit because of uniform convergence, alright, and that term wise limit is 0, right. So if you want, maybe it will be helpful if I write down that so you see if you, for example, you know, if I take let us take for example cos z, okay, which is by definition e power I z plus e power minus I z by 2, okay, and then you calculate modulus of cos z, you get this, okay. You must have probably seen this in a first course in complex analysis, and well, anyway, let me write it down so that it's perhaps, because it's pretty easy. So I put z is equal to x plus iy, so I will get and what I will get is e power ix e power minus y plus e power minus ix e power y divided by 2, okay, and then I use a triangle inequality and write that as greater than or equal to modulus of maybe I use triangle inequality and write this as modulus of e power ix e power minus y minus e power minus ix e power y by 2, okay, and which turns out to be, well, e power minus y minus e power y by 2. This is what I get, and you can see that as the imaginary part of z goes to imaginary part of z is y, and as that goes to infinity, it's clearly this quantity is going to go to infinity, and therefore mod cos z is going to go to infinity. Essentially you will get the same kind of inequality if you also put sin z, okay, and therefore as imaginary part of z goes to infinity, both mod cos z and mod sin z go to infinity, therefore their reciprocals will go to 0, and that is the reason why as imaginary part of tau goes to infinity, these term will go to 0, this term will also go to 0, because it will go to 0 in its modulus, in its absolute value, and therefore term wise the limit is 0, and you can take the limit term wise because the convergence is uniform, alright. So the upshot of all this is the following, namely that so let me write that down. So hence, so maybe I can put this in brackets, thus E3 of tau minus E2 of tau tends to 0 uniform as imaginary part of tau tends to infinity uniformly with respect to real part of tau. Okay, so we get this. So this is what we get for the numerator of the lambda function as imaginary part of tau goes to infinity. A similar calculation can be done for the denominator as well. A similar calculation computation gives for the denominator of lambda of tau, namely it is E1 tau minus E2 tau E1 tau minus E2 tau. If you follow the same procedure, remembering that E1 tau is p tau of half and E2 tau remains as p tau of tau by 2, and do the same thing, what you will end up getting is the following. You will get summation n equal to minus infinity to infinity pi squared by cos squared pi n tau minus pi squared by sine squared by n minus half tau. So you will get this. You just have to follow the same steps and you will get this. And now well, the same argument applies as we decided for this case when the imaginary part of tau goes to infinity. The only difference is that there is a term n equal to 0. The term n equal to 0 is going to completely remove this denominator. So it will, you take a limit, it does not have any effect on this term. So what you are going to get is you are going to get pi squared. Okay, all other terms are good. The only the n equal to 0 term, and that too only this part is going to be unaffected. All other terms will die to 0. Okay, so what you will get is we get E1 of tau minus E2 of tau tends to pi squared as imaginary part of tau tends to plus infinity uniformly with respect to real part of tau. Okay, so if I put these two together, I get that as imaginary part of tau tends to plus infinity, okay, lambda of tau goes to 0 uniformly in real part of tau, which was the original claim. Okay, so thus lambda of tau tends to 0 uniformly in real part of tau when the imaginary part of tau goes to plus infinity. Okay, so so that tells you that at infinity you can extend lambda to infinity, to the point at infinity, by defining it to be 0, and that will extend it continuously. Okay, so that is the that is part of the claim. Okay, now we need to still prove further claims, and I will do that in the forthcoming lectures.